Hello everyone and welcome to this video, and in this video we'll be looking at a SACE 2009 exam question, and this one is orientated around differential calculus. The good thing about this 9-mark question is it allows for the development of answers using technology before developing and proving a conjecture in calculus. So it's going to be quite an interesting question, but quite a straightforward question for the most of it. It's really just towards the end where you start needing to not use technology and actually analyze and interpret patterns. So let's first start off with the 1-mark question. Just to introduce what the question's about, we have a function given on the graph. It's already plotted, as you can see on the right hand side of the screen there, and this function is y equals 1 on x multiplied by e to the x. And what the first question is asking us is to find the x-coordinate of the stationary point visible in the graph. So on this actual exam paper, you can sort of see where the stationary point is, and you can have a pretty good guess of what the x-coordinate is. But just to be on the safe side, it's always good to verify your answer using technology. The good thing about this question is it says find, so we don't need to show what the x-coordinate is, we just need to find it, and find means that we can use technology to be able to come to a conclusion. So on your TI calculator, the first thing you probably want to go and do is actually go into the y equals menu, and you should be able to see this. In fact, yep, there we go. We basically want to put in 1 on x times e to the x into that y equals menu again, and just graph that function. That's a first thing you want to do, because when you get this you can actually use a minimum function, and to find the minimum function, again, you don't need to see the screen for this one, but it's this button here. What you do is you go second function, the blue key, second function, calculate, and you scroll down to the third option, which is minimum. So you go to the left of the actual minimum, so I'm going to go till I see the cursor go across to the left. It's probably, I don't know, choose somewhere like 0.5 for example, x equals 0.5, and then choose maximum and then press enter, and you should end up with x equals 1 and y equals 2.718. So as we can see there, the actual x-coordinate of the stationary point, which of course is this minimum here, which you can see on the actual graph, what you actually found on the TI-84, is actually 1. So we write x equals 1. That's the x-coordinate of the stationary point visible on the graph there. So that's a really easy 1-mark question. Again, you could probably even read it off the exam paper, but it's always good to double check, especially if checking only takes you a couple seconds to plug in the function and use a minimum function there. Something interesting I'll just note here is you can see that y value on your TI-84, the 2.718, that's approximately equal to e, which is Euler's constant, which in context makes sense as well, because when we think about it, we've got 1 on 1, lots of e to the 1, which is going to be 1e to the 1, which is e to the 1, which of course is e, which is around about 2.71. But it's only asking us x-coordinates, so that information is of course redundant, yet interesting at the same time. Now let's go on to the next question, which is asking us to sketch y equals 1 on x squared, and then mark on the stationary point. So I reckon it's about time we try that. So we go to the y equals menu, we can just edit our function, we just go down into the denominator there, and we can just square the term using the power key, and then graph it again. So again, we can use technology here because it's asking us to sketch it, and the best way to do it is to get that. Now, a key thing I probably should have pointed out before, and this really helps when you're using technology, is that whenever you're graphing something or you're having to sketch something, always set your calculator to the domain given on the actual exam paper. This will be very helpful because it's like having an exact mirror image of what you've got to draw. So always set the window size to what is given, because they've given it to you for a reason. So now we've got this function here and we're asked to sketch it. The best way to sketch a function is to have multiple points. There's a few other key ideas, so I'll just write these up down here, but multiple points is what I would consider one of the most important, because that way you get a nice smooth curve, especially for a function like this, which is not linear. Also, set the domain, as I said before. Domain should be as seen on exam paper. And of course, another key consideration when it actually comes to graphing is what I like to call YORO, which is you only rule once. Because it's very important with a function, especially a curved one, that you don't sort of have something like this where you go over again to try and mark out the shape, because it's not mathematically accurate, it's very confusing, and it's not a sketch. That is not a really good way to draw it. Just try it as shown there, one nice smooth curve. Okay, but then also on top of those 3 key points there, which you should be able to see on the board, we've also got this idea of use second function plus table to plot your points on the TI-84. Because it's a really, really great way to save some time. Instead of having to go second function, calc, enter an integer, press enter. There we go. Now we can plot a point. We've got it in a nice tabulated form. So in case you have no idea what I'm talking about, on your TI-84, just hit this blue button here, second function, and then this graph button, which becomes table, and hey presto, you've got a table there which you can follow off of. So I'm going to have a go at plotting a few points. Again, consider the domain when you're plotting a few points. We're always looking at x greater than 0, y greater than 0 here, because that's what's given on the exam paper. All these things are really apparent to you when you start graphing and you start sketching graphs, and it just becomes second nature, and you can do this question easily within a minute, probably, even though it's a 2-minute question. So what we do is we have a really good approximation of some of these points, but we start off with 1, and we get 2.71, which is again e, so actually has the same point there. It's a shared point between the two functions. 2 is 1.8473. 1.8473. Just make sure it lines up. Then we've got 3 is 2.23. And then we've got 4 is 3.41. 3.141. And then we can have an attempt at sketching a nice smooth curve as shown. Again, the more points you have, the better. I would say for a function like this, maybe have about 4 if you can help it. I've got 4 there, but the more the better. Again, don't get carried away though, it's only a 2-mark question. Now we need to label the stationary point. Now the best way to check that we've actually sketched the stationary point accurately, and it's always good to check this while you're going as well, is to obviously use the minimum function before. So again, you can just use that second function, calculate, go into the minimum function, and just work out that you've got it reasonably accurate on there. And the stationary point is 2. So you know I've drawn the graph reasonably accurate, but we can just mark on the value of m there. Okay, so now it's asking us to complete the table below. So we've got the function, and we've already done the first one here, 1 over x etx and 1 over x squared etx. So it's asking us to fill in the x coordinate of the stationary point. For the first one, it was 1. That was the 1-mark question we were given before. And for the second one, as we just found out using the minimum function there, when we had to mark on that value of m for the stationary point, it was 2. Now, for this, you want to obviously go back to your y equals menu, and you can use the minimum functions. There are a few of them. The pattern should become quite obvious. But what I'll do is I'll encourage you to pause the video here, have a go at actually putting them in, and then just play the video once you've had a go at using the minimum function and being able to find it using the TI-84. Okay, so hopefully you had a go and you found, unsurprisingly, that the other two were 3 and 4 using the minimum function. So now what's asking us to do is make a conjecture about the x-coordinate of the stationary point for any function, which is y equals 1 over x to the n e to the x. Now, it's pretty obvious what kind of pattern's happening here. As we can see in the table, in case you haven't actually picked it up here, we've got 1 over x to the 1, the x coordinate, the stationary point being 1, 1 over x to 2, stationary point being 2. So we can see that this value of n actually represents the x coordinate of the stationary point. So what we can write here as our conjecture, again, worth 1 mark, is that the x coord of the stationary point, I'll just abbreviate here because I haven't got a lot of space, but x coordinate of the stationary point for a function in that form would be equal to n. Okay, and the very last thing that it asks us for is to prove the conjecture. So we've got to prove that the x coordinate of the stationary point for a function in that form is indeed n. I mean, we've looked at it in 4 examples, so we've got a pretty good idea that it's probably not quite a fluke, that something's actually happening here that we can prove algebraically. But what we've got to do is we've got to obviously consider how we can show that the stationary point is that value. And that's where it's really important to understand the concept of the derivative. So when the derivative is equal to 0, it means that the slope of the tangent for the function f of x is also equal to 0. So basically you set the first derivative to 0 to find a stationary point. So for this particular example, we will just take the actual function we had before, which is y equals 1 on x to the n e to the x, and we'll differentiate it. So again, we can use product rule here to get the first derivative. And we've got 1 on x to the n. We can use quotient rule there. We differentiate the constant, it becomes 0, 0, multiplied by the denominator is 0, obviously, because 0 times anything is 0. So we end up with negative, and then the derivative of the numerator there, which is x to the n minus 1. And in fact, I'll probably make this slightly easier, just in terms of getting rid of the quotients. But we can actually rewrite this here, y equals 1 on x to the n e to the x, as being y equals x to the negative n e to the x. Again, that's just using a simple rule that you've probably learnt about exponents before. But when we actually differentiate it, it should be a lot nicer now, because instead of having to use quotients and things like that, we can just use power rule for this. So we've got still product rule, but we've got negative n x to negative n minus 1 e to the x as the first term. So again, I just differentiated that using power rule, then multiplied by e to the x, plus the derivative of the second term, which is obviously e to the x, multiplied by, and then the first term as is, to get our derivative. Again, it's a little easier to work with without the quotients, in my opinion. But what we do is we set this first derivative equal to 0. So we've got 0 equals negative n x to the negative n minus 1 e to the x plus e to the x x to the negative n. So at the moment it's looking a bit complex, but we'll easily be able to sort this function into something that we can work with. Again, let's go on to the next slide. And the first thing we probably want to do is actually move this to the other side, because that's a negative term there. So when we move it to the other side, it'll be positive. 2 positive terms, really easy to work with. And that way we can start algebraically rearranging. So we'll end up with n, negative nx. So in fact, because it's negative, it moves to positive. But nx to the power of negative n minus 1 e to the x plus x equals x to the negative n e to the x. And then what we can say is, well, hang on, because we've got e to the x multiplied by the term on each side, so we've got nx to the negative 1, negative n minus 1, and x to the negative n, we can say that these two little bits here must be equal to each other. Again, that's only logical, because of course, if you multiply 2 by 1, you get 2, obviously. If you multiply 3 by 1, you get 3. So, of course, we can obviously say that that one equals that one. So, what we do now is we think, well, if we've got xn to the negative n minus 1, equals x to the negative n, then we can bring this term onto the other side, and we actually subtract it. So I'll just check that we've got space to show this on the board. I might just slightly lower this down. But what we end up with is we end up with nx to the negative n minus 1 take x to the negative n equals 0. Yep. And then after that, well, we can say, hang on, we can represent this as this. And then because we can represent it as that, we can go on to the next step, and we can actually say, well, we need to get a common denominator for the two terms. So what we can do is we can simply multiply that out. Again, we just times by x because that's actually x plus 1 there. We need to get that plus 1, so we multiply by x. And then what we end up with is n take x equals 0. Because we've got a common denominator here of xn plus 1, and we move that to the other side and multiply it by 0, we just end up with n take x equals 0. Hopefully you can see how that works, but again, we're just getting common denominator, we're multiplying this by x, and then from that we're able to move the common denominator onto the other side. Okay, and then lastly, we need to find x, so therefore x, because we move it from that side to the other side, so it's negative x, it becomes positive x on that side, we can say that x equals n, and we just proved our conjecture there. So hopefully this video was relatively straightforward and you were able to follow it. Again, it's just a nice simple little conjecture that you can actually prove using differential calculus. Again, a 9-mark question, a lot of it you can do with technology because of the sort of questions it asks, but then it's just that end bit where you need to differentiate, think about the pattern, how do you prove the pattern, and you end up with something similar to that. Again, you can use the quotient, but I just find it easier to work with negative exponents rather than having quotients in there. But hopefully you found it interesting and you were able to follow along. Again, subscribe if you're interested, and yeah, thanks for listening.